I want to talk a little bit about a project I've been working on with my thesis advisor committee, other members of our machine learning group here. It'll be quite related to what Geir was speaking about as well, where we have some uncertainty in the specification of the network architecture that we're proceeding with. And so we want to come up with a Bayesian approach to try and represent this uncertainty or deal with it. So I'll go over a little bit of the motivation for how we came about this problem, and then we'll go very quickly through the background on Bayesian neural networks, since we've already had an introduction to that today. And I'll present hierarchical models briefly as an idea of how we can start to think about this variable number of parameters or variation in the architecture itself. And depending on time, I'll go into the inference method of reversible jump Markov chain Monte Carlo, which is the approach that we're trying to implement to explore these variable size Bayesian neural networks. And I also have some early results from some of my experiments to show off, just to demonstrate how this can be applied to practical data sets. So as some motivation, when I first started looking into Bayesian neural networks, I came across this concept, this idea that it comes up in the literature every now and then, that the Bayesian approach allows for different models, such as those with different numbers of hidden units or different numbers of hidden layers or other different network implementation choices, to be compared using only the training data. And I saw this idea mentioned more often than I saw papers addressing it. It's nice to see that there are some recent works, as we just saw, that are examining this opportunity with Bayesian neural networks a little bit more. But I wanted to have a look myself, and we had this idea to explore a transdimensional inference approach to try and come up with this automated inference algorithm for handling Bayesian neural networks with an uncertain number of parameters. So here, once again, is an equation that we've seen in both Anna's introductory presentation and Geir's presentation just preceding mine. At the bottom of the slide here, the posterior predictive distribution is one of the products of Bayesian inference, and is of particular interest to us in Bayesian machine learning settings, where we often are more interested in the predictive capabilities of our model than inference about our model parameters themselves. So when we do run our Bayesian inference, regardless of what model we're working with, the two products that we get, again, are this posterior distribution of the model parameters and the posterior predictive distribution for our targets or response data, the Ys. And of course, when you're dealing with a model and you have a functional form for it already, as Geir mentioned, the model can be specified entirely by its parameter vector, which is this theta. And that's what we put our prior distribution over, pair it with a suitable likelihood, and achieve our unnormalized posterior distribution. So my plan was to build up to Bayesian neural networks from the idea of Bayesian linear regression, much as we may build up to classical neural networks from concepts that arise in classical linear regression. But again, I'm going to move quite quickly through these slides to get to the inference method, the inference approach, and focus on that a little bit. But I guess one of the key takeaway points I'd like you to think about as we move through this is, when I talk about getting a joint posterior distribution over the parameter vector theta for this Bayesian linear regression, you can think of this distribution, or rather samples from this distribution, as being essentially linear regression models. So each sample that you draw from your posterior distribution gives you a set of these theta parameters, which are your weights and biases in a regression model. And what we have to assess how well that model explains the data is the posterior score. So this might be thought of as a relative goodness of fit for when you draw a linear regression model from this posterior distribution, you can get an idea of how well it compares to other draws from this distribution or other linear regression models based on that posterior score. And this idea extends upwards to Bayesian neural networks, where we have more or less the same, or rather the same architectural, or rather functional representation of classical neural networks, with our input layer, our variable number of hidden layers, and our network output, and activation functions for the hidden layers and the network output as well. So the big difference being with our Bayesian neural networks now is that we have distributions of parameters for each of these weight and bias terms. And I'm not going to talk too much about the priors. That's something that's been addressed today a little bit, but one of the classic or popular approaches to setting up these neural networks, these black box models, is to use zero-centered Gaussians, and most of the specification or flexibility in your neural network is based on the within these prior Gaussian distributions, the variance parameter sigma squared, that gives you a spread of potential parameter draws from these prior distributions. So once you have an idea of a Bayesian neural network model, in order to extend that to having freedom of architecture specification, where we have uncertainty in what size of neural network we may be interested in, we need to talk about hierarchical models. Hierarchical models are those where all of the parameters in your model are not necessarily independent on each other. So in the Bayesian neural network introduced on the previous slide, we're again assuming this perhaps naive independence between parameters, which means that we can that all of these parameters exist on the same level. But if there is dependence between parameters in our model, then we need to distinguish between low-level parameters and high-level parameters, depending on how many levels we have to our hierarchical model. So here I represent a hierarchical model by introducing these precisions as the inverse of the variances that go into our prior distributions for the weights and the biases. But what I really want to focus on instead is the introduction of, in the two red nodes here, these hyperparameters that are going to control the architecture of the Bayesian neural network. So we might think of the number of hidden layers or the network depth as being specified by a parameter L, and the width of those hidden layers as being specified by a parameter K. These are both discrete parameters, and we need to give them a suitable discrete distribution to act as the prior. And essentially, once we establish that we're proceeding with a neural network model with these weights and bias parameters and the architecture parameters L and K, which are going to control how many hidden neurons we have in each layer and how many hidden layers we have in our network. Now we have what you may refer to as a transdimensional model, where as we think of sampling from this distribution of Bayesian neural network models, we're going to end up with samples that correspond to neural networks of different size. So this results in a slightly more involved posterior distribution, because our prior over the network weight and parameters represented by theta are now conditional on these architecture parameters. And so we need to involve their prior distributions as well, the prior over the network width and the network depth. And so this is essentially, we arrive at a defined model for our Bayesian neural network that can be a variable size. But it's quite another thing to actually do anything with this, because of course, we don't really have a convenient analytical representation of these Bayesian neural networks even before we start to introduce variation to the size of the network. So in the interest of time, I'll have to go fairly quickly through this, but as Geir mentioned, one of the approaches to working with Bayesian neural networks is the MCMC methods, Markov chain Monte Carlo. And if you are familiar with Markov chain Monte Carlo, you're probably familiar with the Metropolis Hastings algorithm, where we have a Markov chain for which the states of the Markov chain represent samples from our unbiased posterior distribution. And if we define our Markov chain carefully, then we're guaranteed to sample from the exact posterior distribution. And then we just need to run our Markov chain long enough to get an appropriate number of samples to get a reasonable approximation of our distribution. And the key points in the Metropolis Hastings algorithm is that you are proposing your next state, theta prime, the next stop in the Markov chain, based on your current state, theta, and defining an acceptance probability that will assure you or give you the ability to properly sample from this posterior distribution. So it's essentially the mechanism is to propose a new state and then either accept or reject it based on an appropriate acceptance probability. So if you are familiar with Metropolis Hastings, then it's a little bit easier to extend up to what we call the reversible jump Markov chain Monte Carlo algorithm. Metropolis Hastings is actually a special case of reversible jumps, or the Metropolis Hastings green algorithm. And what actually ends up being a convenient result of the MHG approach to MCMC is that we can concern ourselves with models of varying size, where that vector theta of our parameters can change in size from one proposal to the next. And we still have a mechanism for defining an acceptance probability appropriately so that we do guarantee asymptotic sampling from our correct unnormalized posterior distribution. So I don't want to talk too much about reversible jump Markov chain Monte Carlo. I really just wanted to introduce sort of the conceptual idea behind this. But if you think of Metropolis Hastings and try to extend this to the reversible jump algorithm, where we can draw these proposals that are of a higher dimension or a different dimension for our parameter vector, the main feature that goes into that is that along with our current state theta, we also need to draw additional random numbers that we call u here in order to match the dimension, the desired dimension of our new proposal, which is defined by, in this case, this indicator variable k. And so I want to skip ahead to an example here where we are sampling one of these transdimensional Bayesian neural networks based on a flexible, or rather variable, number of hidden layers. So in the diagram on the left, we have our current state of our Markov chain corresponding to a Bayesian neural network with 13 weight and bias parameters. So the dimension is 13. And what we're looking to do is propose a new Bayesian neural network, our next state in the Markov chain, theta prime with 25 weight and bias parameters, of which 13 are brought over from our previous network. And then we're going to draw the additional 12 from as these u random numbers. And those are just going to come from the prior distributions over the weights and biases for the neural network. With the reversible jump algorithm, we have an opportunity to use this G deterministic function to edit our proposal. And so you're afforded a lot of flexibility in terms of how you define your proposals, ideally so that you can get a reasonable acceptance probability and actually sample efficiently from this distribution, because as was pointed out, MCMC methods are very computationally intensive. And reversible jumps is sort of notorious for being particularly difficult to implement with a high acceptance probability. Now, this proposal mechanism actually is not going to give you a very high acceptance probability alone, because you've essentially just introduced an entirely random layer to your neural network. You have some really convenient specification, perhaps, in the parameters that you've brought over from the previous network. But by introducing this new layer, the functional representation of your feature data is probably going to give outputs that don't match the likelihood for the data very well. And so acceptance probability is likely to be extremely low. And again, just in the interest of giving a very high-level conceptual overview of what we have done to try and make this work, is we're using something called delayed rejection sampling, which you might think of as lightly training our newly proposed state of the Markov chain, the newly proposed network, to increase the chance of accepting a proposal. And by doing this, we actually are able to introduce some MCMC methods that use the gradient to bring us a little bit closer to more classical machine learning approaches. I don't think I have much time to talk about that, but if you're interested in perhaps asking during the question period, or we can talk after the presentation today, I can give you some more information about what that looks like. I'll just end on sharing a little bit about one of the experiments I've been running on the Boston housing data set. So I've set up one of these transdimensional Bayesian neural networks with a variable number of layers to try and perform the classic regression on this rather small data set, 13 input features and a training set of 256 samples. And basically what you're trying to do is, it's a regression problem to try and minimize your root mean square error on a test set based on the output of the neural network. And so the key detail here is that when I implemented this particular sampling, I specified a variable L controlling the number of hidden layers in the network that could vary between 1 and 4 layers. And so as the Markov chains run in parallel, they occasionally visit Bayesian neural networks of different sizes. And at the end of the run, you can marginalize over all of your training samples. And that's this value here, which gives us our RMSE of 0.21. Or you can marginalize by individual chains, or for example, by number of layers. And so I thought this would be one interesting look to see if we get some better representation, or rather better RMSE results based on the number of layers for the neural network. But also, really what's happening here is that because we've specified some uncertainty ahead of time, we've said that we don't really know what the most appropriate network architecture is for this neural network, we can marginalize over all 4 of them and essentially abstract that network design option away from us. And so independent of the individual results and whether or not they imply that one particular parameter or architecture specification is better than the other, we do at least get the opportunity to marginalize over all of those different architectures without having to specify one individually. So I hope that I was able to represent the conceptual introduction to this idea reasonably. I have some further reading that I'd recommend here in case you're interested in Bayesian neural networks or some of the modern approaches, or at least one modern approach that's looking at the ensembling power of these BNNs. But I think that I'll end the presentation there. We can turn it over to the question period